I'm from Timeular, and I will show you today how you can use a IoT device to track your time. So first of all, let's give me a short introduction, what we do at Timeular and who I am. So our goal at Timeular is to help you to manage your time. And you might ask, why is time management important? So yeah, as you all know, there are only 24 hours in a day. And we think it's super important and for everyone to make the most out of their time. Something that is probably very remarkable about us as a startup is that we have a hardware IoT device, which you can see here in the middle. We call it a tracker, and I will explain more in detail later on. But also that we have been fully remote since 5 years already, so right from the get-go. Some facts about me. So I'm a co-founder at Timeular, and I'm the CTO and also responsible for product. My technical background is I'm coming from the iOS and generally from the mobile scene, and I've done a lot of Bluetooth Low Energy related projects in the past, which helped me a lot when starting out with Timeular. Before we dive into the presentation, I will give you a rough overview about our stack. So as I already mentioned, we have the hardware device, which we call the tracker. Then we have native Windows app, native macOS app, a native Linux app, iOS and Android app. I deliberately put native into air quotes, and I will explain later on why I did so. And on the backend side, we have a couple of microservices, which we host on Amazon AWS. Okay, let's start with the tracker. So first of all, explain you how the tracker actually works. So the tracker has 8 sides and is connected via Bluetooth Low Energy to either your smartphone or your computer. You can assign projects, activities, clients, or whatever to each side of the tracker. And once you put the tracker on one side, it will start tracking the corresponding client or project. So we make time tracking really easy. So it's just a matter of putting the tracker on the right side. And internally, the tracker is based on a platform of Nordic, and the platform is called NRF52 more specifically. And additionally to the Nordic platform, we also use a gyroscope to detect the position, how the tracker is laying on your desk. You might ask why we choose to even go through the hassle to build the hardware. So we've tried a lot of time tracking software and time management software in the past by ourselves. And one thing that always was really annoying to us is that on purely software-based products, it's just like one other app that you have on your phone, one of 50 browser tabs that you have open. So ideally, you do time tracking in real time. But if it's just one of those many apps that you use at the same time, you simply forget about it. So it's super hard to build a good habit of time tracking if you're only using a software product. We thought that building a hardware which acts as a remote might be really helpful, and it turned out to be. But one thing that we discovered along the way, having the hardware constantly in front of you at your desk is also a good reminder on what you should focus on right now. And as a small bonus point that you can see in my slides here, when you build a hardware that is customizable, you get a lot of customer love on Instagram. And it's always a pleasure to get a mention and see how our customers customized our tracker. So those are just some examples that our customers shared with us. So so building a hardware device obviously has also huge implications on the software stack that we will be using. So as with most startups, we would have loved to build a web app because it allows us to really iterate fast. But having this hardware device, which communicates via Bluetooth Low Energy with your smartphone or your computer, required us to build native apps. Building fully native apps, meaning Objective-C or Swift on macOS, something on C++ or C# on Windows, and so on, is simply not sustainable for a small startup. So we went with a hybrid approach. Our goal was always to share as much code as possible, but where it makes sense, we dove down and implemented some parts in native. To be more concrete, we built our complete Bluetooth Low Energy implementation on the different operating systems natively. And on top of that, we have a shared code base, but I will explain you more about that later on. And yeah, generally in today's talk, I will give you an overview how like the complete system works, meaning starting something with the hardware device and ultimately ending up in the cloud and syncing this event to all of your devices in real time. So the first step of the journey is the tracker. So usually when you stop working or in the morning before you begin working, the tracker will be in its base. That is the small black thing that we see here. And this means the tracker is currently sleeping and not doing anything. So to start your day and start time tracking, you simply remove the tracker from its base and it will wake up. Once it wakes up, it will start advertising. And here I need to explain you some details about Bluetooth Low Energy or how like Bluetooth Low Energy in general works roughly. So there are two roles in a Bluetooth Low Energy relationship. There is the central and the accessory role. In our case, the tracker is the accessory, and the like desktop app or mobile app is the central. So once the tracker is put out of its base on the desk, it will start advertising, and the central devices, meaning desktop app or mobile app, are constantly looking if there is any tracker nearby that they could connect to. Once they see a tracker, they will connect to it. And advertising, sorry, I need to mention that. Advertising means simply shouting out to the world, hey, I'm a Bluetooth Low Energy device. You can connect with me, and I offer you the following services. And services are, in the Bluetooth Low Energy world, are characteristics. And characteristics usually like transport a certain value. So in our case, one example would be the charge of the battery. So how much charge is left for the battery, but also which side is currently facing upwards. So once you put the tracker out of the base, it wakes up. One central device will connect to it. It will subscribe to the site characteristic, and once the tracker is put on a certain site, it will send the site to the desktop app. So we have now two cases. So the first case could be that our desktop app takes the central role and is connected to the tracker or the mobile app. Let's go for the desktop app first. So once the desktop app connected to a tracker, it will read the site characteristic and see if the tracker is laying on any side. If it detects one of the 8 sides, it will do a simple mapping between side and activities. So in our software, you can assign like different activities to each side of it, and then it will start tracking this certain activity. So in this case, it's deep work. But also at the same time, it will make a call on our backend and start the tracking on the backend, so it can be synchronized to all your other devices. Because one thing that's also important to note here, that the tracking and all the data is in sync between all of your devices in real time, all the time. To give you more in-depth overview about the architecture, so we support macOS, Windows, and Linux as platforms, and our stack is native Bluetooth Low Energy implementation for all 3 platforms. Our native Bluetooth Low Energy implementation is open source, so you can have a look at it at GitHub. One like interesting fact here to mention is the Chromium team, like the browser team, is working on Bluetooth Low Energy support in the browser, and it's currently already available as a preview. And once they started working on it like a couple of years ago for their Windows implementation, they referenced our Bluetooth Low Energy implementation a couple of conversations, and that was actually really flattering. On top of the native Bluetooth Low Energy implementation, we have shared code. So first of all, we share code, the complete like desktop app code between Windows, Mac, and Linux, but also we share the complete business logic between desktop and mobile. So yeah, this architecture simply allows us to move fast and also build all of our product with a relatively small team. And for this shared code base, like we use React as a like runtime to run our app on the desktop. And inside React, we have Electron. And inside Electron, we have a React application, which is written in TypeScript. So we started out with JavaScript, but like 2 years ago, we migrated all of our code base to TypeScript. So all the mobile app could also, or the mobile phone or app could also be in the central spot, meaning the mobile phone connects to your tracker. As I said earlier, we share the code base, which is written in TypeScript for the business logic, also with mobile. And the UI is written in React Native. And again, the Bluetooth stack is written in like in native code in Objective-C for iOS and in Kotlin for Android. All in all, it works very similar to the desktop way, although the whole Bluetooth and background handling implementation was way more challenging on mobile, simply because background tasks are way more restricted on mobile. So you need to take more precautions here to make sure that your app is running, or get started once you receive updates from the Bluetooth device. So once the mobile app reads the site characteristic from the tracker, it will also start the tracking locally and then notify our backend. So the final part of this whole system is our backend. And on the backend, the start tracking event arrives at our time tracking service, which is one of our many services in our microservice architecture, and is also relayed to other services that might be interested in that event, and also put on a WebSocket connection. So all of our devices establish a WebSocket connection to our cloud or backend, so we are able to sync them in real time. And some general overview about our backend infrastructure. So as I said already, we use a microservice architecture. All of our microservices run inside Docker. The Docker containers are already orchestrated by Kubernetes, and we already heard a short and very good explanation about Kubernetes beforehand. We run at least 2 instances of every microservices at any given time. This whole system is hosted on Amazon AWS. And for languages, we use Kotlin, Rust, and Go. We've been using Kotlin since the start. And we've introduced some Go services and later on Rust services. And currently, we are investing more and more into Rust, and we will phase out all the Go services at some point. So going forward, we will continue using Kotlin and Go. And for the event handling and event queue, we use RabbitMQ as a queuing service. Some outlook. So as I said earlier, the Chromium team is working on Bluetooth Low Energy support in browsers, and this would actually allow us to port our application to the browser. It's already kind of a web application running in Electron, so having this cross-platform and lots of shared code approach would allow us to port it relatively easily, though it will take some time until Bluetooth Low Energy support is broadly available to the major browsers and also in a business context. Up until now, or up until then, we could actually use a hybrid model, meaning we could build small native applications for the different platforms, but move all the visualizing the data, managing data, and everything UI heavy to the web. And this would allow us to simply have shorter and faster iteration cycles. A short recap. I think the biggest takeaway here is that a seemingly very simple task, so start a tracking from a hardware device and sync it in real time to basically all of your devices, is actually quite complex and involves a lot of steps and lots of moving parts. And I think the biggest accomplishment of our engineering team is that we managed to build this native or air quote native apps for lots of different platforms. And support lots of different platforms with a rather small team. So we currently are 3 engineers, front-end engineers, and 2 back-end engineers. So 5 people in total building this complete system.